Hello. In this video, we'll be reviewing some key concepts in sequences and polynomials. By the end of this session, you'll be able to, first, identify and work with different types of sequences, including arithmetic, geometric, Fibonacci, and harmonic sequences. Second, perform operations on polynomials, such as division, and apply important theorems like the remainder and factor theorems. Let's get started with our first topic, sequences. Our first objective is to understand and work with different types of sequences. Let's begin with the most common ones. First, we have the arithmetic sequence. An arithmetic sequence is a list of numbers where the difference between consecutive terms is constant. This constant difference is called the common difference, denoted by phi. For example, in the sequence 21, 18, 15, the common difference is -3. You subtract 3 to get from one term to the next. Next is the geometric sequence. In a geometric sequence, each term after the first is found by multiplying the previous one by a fixed, non-zero number called the common ratio, denoted by r. For instance, in the sequence 5, 10, 20, 40, the common ratio is 2. You multiply by 2 to get the next term. Then there's the Fibonacci sequence. This sequence starts with 0 and 1, and each subsequent number is the sum of the two preceding ones. It's a very famous sequence found in nature. So, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so on. Finally, we have the harmonic sequence. A harmonic sequence is defined by the reciprocals of an arithmetic sequence. If you take the reciprocal of each term in a harmonic sequence, you get an arithmetic sequence. For example, the sequence 1/3, 1/8, 1/13, 1/18 is a harmonic sequence because its reciprocals 3, 8, 13, 18 form an arithmetic sequence with a common difference of 5. Now that we've reviewed these types, let's apply this knowledge to some problems. Let's tackle a few problems to solidify our understanding of sequence types. First, consider the sequence -12, -7, -2, -3. We need to determine what concept to use to find the fifth term. Let's test if it's an arithmetic sequence. We'll check the difference between consecutive terms. The difference between the second and first term is -7 minus -12, which is 5. The difference between the third and second term is -2 minus -7, which is also 5. But the difference between the fourth and third term is -3 minus -2, which is -1. Since the difference is not constant, it's not an arithmetic sequence. Let's test if it's a geometric sequence by checking the ratio. The ratio of the second to the first term is -7 divided by -12, which is 7/12. The ratio of the third to the second term is -2 divided by -7, which is 2/7. Since the ratio is not constant, it's not a geometric sequence. What about a Fibonacci-like sequence? In a Fibonacci sequence, each term is the sum of the two before it. Let's see. -12 plus -7 is -19, not -2. So it's not a Fibonacci sequence. This sequence doesn't fit the standard definitions. It's possible there's a typo in the problem, or it's a more complex pattern. However, based on the options provided, none of the standard sequence types apply perfectly. This highlights the importance of checking the definitions carefully. Let's look at another one. Which of the following is not a geometric sequence? We'll check the common ratio for each option. For option A, 10 divided by 5 is 2, 20 divided by 10 is 2, and 40 divided by 20 is 2. The ratio is constant, so this is a geometric sequence. For option B, 22 divided by -11 is -2, -44 divided by 22 is -2, and 88 divided by -44 is -2. The ratio is constant, so this is a geometric sequence. For option C, 6 divided by 2 is 3, 18 divided by 6 is 3, and 54 divided by 18 is 3. The ratio is constant, so this is a geometric sequence. For option D, 8 divided by 3 is 8/3, 13 divided by 8 is 13/8. Since the ratios are different, this is not a geometric sequence. In fact, it's an arithmetic sequence with a common difference of 5. So, the correct answer is D. We have successfully identified different types of sequences. Now let's move on to finding specific terms in a sequence. We'll start with arithmetic sequences. The formula for the nth term of an arithmetic sequence is a sub n equals a sub 1 plus the quantity n minus 1 times d. Here, a sub n is the term you want to find, a sub 1 is the first term, n is the term number, and d is the common difference. Let's find the 50th term of the sequence 3, 7, 11, 15. First, let's identify our values. The first term, a sub 1, is 3. The common difference, d, is 7 minus 3, which is 4. We want to find the 50th term, so n is 50. So a sub 1 is 3, d is 4, and n is 50. Now we plug these values into our formula. A sub 50 equals 3, plus the quantity 50 minus 1 times 4. This simplifies to 3 plus 49 times 4. 49 times 4 is 196. So a sub 50 equals 3 plus 196. The 50th term is 199. Let's try another one. The 5th term of an arithmetic sequence is 11, and the 10th term is 41. What is the first term? This problem gives us two terms and asks for the first. We can set up a system of equations using our formula. For the 5th term, we have a sub 5 equals a sub 1 plus 4d, and we know this equals 11. For the 10th term, we have a sub 10 equals a sub 1 plus 9d, and this equals 41. Now we can solve this system. A simple way is to subtract the first equation from the second. Subtracting the equations gives us 5d equals 30. Dividing by 5, we find that the common difference, d, is 6. Now that we have d, we can substitute it back into either equation to find a sub 1. Let's use the first one. A sub 1 plus 4 times 6 equals 11. This means a sub 1 plus 24 equals 11. Subtracting 24 from both sides, we get a sub 1 equals minus 13. So the first term of the sequence is minus 13. We have successfully found terms in arithmetic sequences. Let's now look at finding terms in geometric sequences. The formula for the nth term of a geometric sequence is a sub n equals a sub 1 times r to the power of n minus 1. Here, a sub n is the term you want, a sub 1 is the first term, r is the common ratio, and n is the term number. Let's find the 7th term of the sequence 2, 6, 18, 54. First, let's identify our values. The first term, a sub 1, is 2. The common ratio, r, is 6 divided by 2, which is 3. We want to find the 7th term, so n is 7. So a sub 1 is 2, r is 3, and n is 7. Now, we plug these values into our formula. A sub 7 equals 2 times 3 to the power of 7 minus 1. This simplifies to 2 times 3 to the power of 6. 3 to the power of 6 is 729, so a sub 7 equals 2 times 729. The 7th term is 1458. We have now successfully found terms in both arithmetic and geometric sequences. Next, let's learn how to find the sum of a finite number of terms in a sequence. For an arithmetic sequence, the sum of the first n terms, s sub n, is n divided by 2 times the quantity a sub 1 plus a sub n. This formula is very intuitive. It's the number of terms times the average of the first and last terms. Let's find the sum of the first 16 terms of the arithmetic sequence. 1, 5, 9, 13. We know n is 16 and a sub 1 is 1, but we don't know a sub 16. So our first step is to find it using the nth term formula. The common difference d is 4. So a sub 16 equals 1 plus 15 times 4, which is 61. Now we have all the pieces for our sum formula. S sub 16 equals 16 divided by 2 times the quantity 1 plus 61. This is 8 times 62, which equals 496. Now for geometric sequences. The sum of the first n terms, S sub n is S sub 1 times the quantity 1 minus r to the n, all divided by 1 minus r. Let's find the sum of the geometric sequence 3, 6, 12, 24, 48, 96. First, let's identify our values. The first term, a sub 1, is 3. The common ratio, r, is 2. And by counting, we see there are 6 terms, so n is 6. So, a sub 1 is 3, r is 2, and n is 6. Now we plug these into the formula. S sub 6 equals 3 times the quantity 1 minus 2 to the 6th, all divided by 1 minus 2. 2 to the 6th is 64. So we have 3 times negative 63 divided by negative 1. This simplifies to 189. We have now found the sums of both arithmetic and geometric sequences. Now, let's shift our focus to polynomials. Our second objective is to perform operations on polynomials and apply key theorems. First, what is a polynomial? A polynomial is an expression consisting of variables and coefficients that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents of variables. Let's look at some examples to make this clear. Consider the expression 4x cubed plus 9x minus 5x squared plus 7. This is a polynomial. The exponents are all positive integers. Another example is 2x to the 5th plus x squared plus x cubed plus 2x plus 5. This is also a polynomial. Now, let's look at something that is not a polynomial. The expression 1 divided by the quantity x squared plus 3x plus 6 is not a polynomial. Why? Because the variable x is in the denominator, which is equivalent to having a negative exponent, x to the power of minus 2. Polynomials cannot have negative exponents. So to recap, a polynomial must have only non-negative integer exponents. We have now successfully identified what a polynomial is. One of the most important operations with polynomials is division. We'll start with a method called synthetic division. Synthetic division is a shortcut for dividing a polynomial by a linear factor of the form x minus k. Let's look at a common mistake. Gabriel used synthetic division to divide 5x squared minus 16x plus 4x cubed minus 3 by x minus 2. He got a remainder of minus 19. What was his error? There are 2 crucial rules for setting up synthetic division. First, the polynomial must be written in standard form, with terms arranged in decreasing order of their exponents. Second, you must include a 0 for any missing terms. Gabriel's polynomial is 5x squared minus 16x plus 4x cubed minus 3. In standard form, this should be 4x cubed plus 5x squared minus 16x minus 3. Gabriel did not arrange the terms correctly. Let's see if there's another error. The divisor is x minus 2. For synthetic division, we use the value of k, which is 2. Gabriel used 2, so that part is correct. The coefficients of the polynomial are 4, 5, minus 16, and minus 3. Gabriel's first row of numbers should be these coefficients. Let's check his solution. Gabriel's first row is 5, minus 16, 4, minus 3. This is incorrect. He used the coefficients in the wrong order. This is the second error. So Gabriel made 2 errors. He didn't arrange the terms in decreasing powers of x, and he didn't write the numerical coefficients properly. This corresponds to options 2 and IV. This example shows how important it is to follow the setup rules for synthetic division. We have now identified common errors in polynomial division. Let's continue with polynomial division, but this time using long division. We will divide 5x squared plus 14x minus 24 by x plus 4. Long division of polynomials is very similar to long division of numbers. We focus on the leading terms. First, we divide the leading term of the dividend, 5x squared, by the leading term of the divisor, x. This gives us 5x. This is the first term of our quotient. Next, we multiply this quotient term, 5x, by the entire divisor, x plus 4. This gives us 5x squared plus 20x. This is the process used to obtain the second line in the long division setup. So the answer to question 40 is multiplying 5x by x plus 4. Now we subtract this result from the original polynomial. 5x squared minus 5x squared is 0. 14x minus 20x is negative 6x. We bring down the next term, minus 24. We repeat the process. Divide the new leading term, minus 6x, by the divisor's leading term, x. Negative 6, x divided by x, is negative 6. This is the next term of our quotient. Multiply minus 6 by the divisor, x plus 4. This gives us minus 6, x minus 24. Subtracting this from our current polynomial, we get minus 6x minus negative 6x, which is 0, and minus 24 minus minus 24, which is also 0. The remainder is 0. So the remainder is 0, the divisor is x plus 4, and the quotient is 5x minus 6. We have now successfully performed polynomial long division. Let's explore two powerful theorems that simplify polynomial division, the remainder theorem and the factor theorem. The remainder theorem states that if a polynomial p of x is divided by a linear factor x minus k, the remainder is equal to p of k. In other words, to find the remainder, you just plug the value k into the polynomial. Let's use this to find the remainder when p of x equals 4x squared plus 2x minus 15 is divided by x minus 2. Here, our divisor is x minus 2, so k is 2. According to the remainder theorem, the remainder is p of 2. So, the expression that gives the remainder is p of 2. We have now applied the remainder theorem. The factor theorem is a direct consequence of the remainder theorem. It states that a linear factor x minus k is a factor of a polynomial p of x if and only if p of k equals 0. In other words, if the remainder is 0, the divisor is a factor. Let's use this to find the value of p of 3 for the polynomial p of x equals 2x cubed plus 3x squared minus 5x minus 12. We simply substitute 3 for x in the polynomial. P of 3 equals 2 times 3 cubed plus 3 times 3 squared minus 5 times 3 minus 12. This simplifies to 2 times 27 plus 3 times 9 minus 15 minus 12, which is 54 plus 27 minus 15 minus 12. Adding and subtracting, we get 54, so p of 3 is 54. This means that if we were to divide p of x by x minus 3, the remainder would be 54. We have now applied the factor theorem. Let's conclude with a word problem that combines our knowledge of arithmetic sequences and sums. A display of cans on a grocery shelf consists of 20 cans on the bottom, 18 cans in the next row, and so on in an arithmetic sequence until the top row has 4 cans. How many cans, in total, are in the display? This problem is asking for the total number of cans, which means we need to find the sum of an arithmetic sequence. The sequence of cans per row is 20, 18, 16, and so on, until the last term is 4. Let's identify our knowns. The first term, a sub 1, is 20. The common difference, d, is 18 minus 20, which is minus 2. The last term, a sub n, is 4. So, a sub 1 is 20, d is minus 2, and a sub n is 4. To find the sum, we need to know the number of terms, n. We can find n using the nth term formula. A sub n equals a sub 1 plus n minus 1 times d. Plugging in our values, we get 4 equals 20 plus n minus 1 times minus 2. Subtracting 20 from both sides gives minus 16 equals minus 2 times n minus 1. Dividing by minus 2, we get 8 equals n minus 1. Adding 1 to both sides, we find that n is 9. There are 9 rows of cans. Now we can find the total sum using the sum formula. S sub n equals n over 2 times the quantity a sub 1 plus a sub n. Plugging in our values, S sub 9 equals 9 over 2 times the quantity 20 plus 4. This is 9 over 2 times 24. 24 divided by 2 is 12, and 9 times 12 is 108. So there are a total of 108 cans in the display. This problem demonstrates how we can combine different formulas to solve a real-world application. We have now solved a word problem involving arithmetic sequences. Let's quickly recap what we've covered today. We started by defining and identifying different types of sequences. arithmetic, geometric, Fibonacci, and harmonic. We learned how to find the nth term of both arithmetic and geometric sequences using their respective formulas. We also learned how to calculate the sum of a finite number of terms for both types of sequences. Then we moved on to polynomials. We defined what a polynomial is and practiced dividing them using both synthetic and long division. Finally, we explored the powerful remainder and factor theorems, which provide shortcuts for finding remainders and identifying factors. Mastering these concepts is fundamental for your continued study of algebra. Keep practicing, and you'll build confidence in solving these types of problems. Thank you for watching.